Welcome to I Machine Learning's class. Today we have session 8. We're going to learn the k nearest neighbors algorithm. This algorithm is actually pretty simple and intuitive, yet very effective. Now let's first get some intuitions around this k nearest neighbors algorithm. We're going to show the zeros map. On this map, we're seeing the houses that are available for sale in the Fairfax County, Virginia, based on Zillow's information. All the blue boundary lines indicates the boundary of Fairfax County in Virginia, and all the red dots on the map indicates the locations where you may see one or multiple houses are available for sale on Zillow. With such information on the map, naturally people may ask two questions. First, when you see each dot or each house on the map, you may be curious what is the zip code or school zone for that particular house. You can tell this type of question is classification. You may also ask a second question. What is the price of price appreciation for a certain house over the last year? You can tell this type of question belongs to the regression question. With the k nearest neighbors algorithm, which is pretty simple yet effective, we can answer both the classification and regression questions. As I said earlier, we are using the house available for sale on Zillow in Fairfax County for intuition development. Um, Here you are seeing the actual zip code boundaries in the Fairfax County. For now, let's just focus on two zip codes, 22102 and 22101, and also make things simpler. Let's ignore all the other neighborhoods, all the other zip codes. And for now, we only have two classes. One class is three observations indicated by the red dots in the 22102 zip, and the other is three observations in the 22101 zip code. So all the six dots, either red or blue, are all the training data we have. We also know that the average house price appreciation for the blue dots is about 5.1% in the last year, and the average house price appreciation for red dots is 8.7 in the past 1 year. Now you get a new observation, which is indicated by the purple triangle. Now we want to ask a question. First, which zip code is most likely that the purple triangle is associated with? Thanks to our visual system and our brain, for us, just look at the map, we can easily answer the question, right? So the purple triangle, the new data, based on our visual inspection, we can tell almost immediately it belongs to the 22102 zip code. This is pretty straightforward thanks to our visual system and our brain. And now the second question is, what is going to be likely the house price house price appreciation for the purple triangle? If we apply the principle of similarity, and we believe that the house in the same neighborhood or in the same zip code is more likely have the same price appreciation relatively to other zip codes and to other neighborhoods. And we also like to see that is the purple triangle for its house appreciation is more likely to be similar to those for the red dots. So we're just using the house available for sale on the map in the Fairfax County to get intuition around the K nearest neighbors. I think you have get the idea. So the whole idea for the K nearest neighbors is you believe there's similarity between you and your neighbors so that you can make a decision either in terms of classification or regression based on your neighbor's information. So that's the idea, the core idea of the K nearest neighbors. As we know, the KNN, which is a short name for the K nearest neighbors, can do both classification and regression. Here is the formal setup of how the algorithm works for both type of problems. First, let's define the K, the number of nearest neighbors we want to look up to a new sample. Once we know that, we just search around the new sample based on the training data, available data. If this is a classification question, we find the majority vote of the K nearest neighbors in the training data and assign that as the class for the new observation, new sample. If this is a regression problem, we still need to find the K nearest neighbors, then take the average, either simple average or certain weighted average based on the distance between the new sample and the neighbors, and use the average in the samples, uh, in the average of the K nearest neighbors in the training data to determine the value, appropriate regression value or the predicted target value for the new sample of interest. Say now I think you can see that is the KNN method does not really do much with the training data, does not really do any eager aggressive training with the training data. It's more using the training data as a reference, trying to extract similarity or certain patterns in the training data and use that as the basis for prediction for the new samples that we're trying to predict. With that understanding of and walkthrough of the KNN algorithm, now we have two questions to answer. The first question is, who are the neighbors? How do we define the neighbors? The second question is, we talk about we need to choose a K, the number of neighbors to check, and what is the, the proper value of K we should use. For the rest of the session in today's lecture, we're going to answer the two questions. There are different ways using different distance metrics to define who are the neighbors. One of the most commonly used one for numerical features, i.e. independent variables, is called the Euclidean distance, which for most of us you're probably already familiar with. Let's first look at the two-dimensional example. We have two observations. One has x1, x2 correspondingly to the horizontal and vertical axis. The other observation has x1 prime, x2 prime. And we can easily to plot those 2 points on a two-dimensional chart as we see here. And we know the distance of the two dots, 2 points on the plane is simply this formula. We sum up the differences on each dimension and then take the square root. That is just the definition of Euclidean distance. And with math, we can easily go into higher dimensions. It's not just limited to 2 dimensions. We can have n dimensions. Now it becomes difficult to plot this on paper, but the definition still holds. We just extend, add additional dimensions to the formula, and then we can still calculate such distance by the definition. So this is the first very commonly used distance definition. And to be aware here is, earlier when we look at the house for sale example, we talk about the distance, we talk about neighbors in terms of geographic location, geographic distance. But when we are using the KNN algorithm, the distance, the space is not just limited to the geographic distance or geographic space. Indeed, we can calculate the distance for features. Just give a few examples. We experimented with the diabetes data set a few weeks ago. And in that data, in that problem, we have features such as age, BMI, blood pressure, and serum measure 1, 2, 3, 4, 5, 6, and so on and so forth. So we have different features, different independent variables into that particular problem. And we also have worked on the handwritten digit problem. With that, we have 28 by 28 pixels in each image. If we flattened the image into 1 dimension, basically we can have a vector of pixels, first pixel, second pixel, all the way up to 784 pixels for each image. In this case, our features are the gray labeled pixels for each image. And we can also think about house price. On previous page, I purposely talked about house price appreciation, not house price, because house price appreciation is more linked to the location of the house. But when we talk about a particular house price, it's not just the location, it's also about certain features with the house, such as which year was the house built, and the number of bedrooms for the house, and also the size and lot size and materials being used in the house. So just look at the 3 examples. I just want to have you sense that we can also measure the distance for features which are not necessarily the geographic features or geographic locations. Also, to point out, because we're dealing with different features, it often has a need to rescale the features into the similar range, such as 0 to 1. One easy way to do that is you take one particular feature and you scale it by the range, which is the maximum to the minimum, and then you using this formula, it will help you to convert all the features into the range of 0 to 1. The importance or benefit of converting features into similar scale is to prevent that certain feature, because its magnitude is bigger, can dominate the distance measure. For instance, if we talk about the house price example, we may deal with number of bedrooms, like 1 bedroom, 2 bedroom, 5 bedrooms, 7 bedrooms. While we'll talk about size of a house, living space, the size of a house, we probably talk about 1,000 square feet, 2,000 square feet, and even 5,000 square feet. So if we are using different features at very different magnitude, it's going to scale, it's going to kind of distort it, it's going to distort the meaning of distance. So that's why we need to rescale different features into the same kind of range 0 to 1 in order to make the Euclidean distance meaningful for the KNN algorithm. A second commonly used distance metric is called a Hamming distance. This one is useful and applicable for categorical features. Its definition is just like this. Essentially what it does is it compares whether two observations have same or different label for each feature. If the label for the different observations is consistent, then the distance is zero, no difference, no distance. If the labels for two observations on the same feature is different, then we put the 1 as the distance. We just look at each feature one by one, compare two observations on that feature one by one, then later we sum up the total difference, the sum of individual comparisons becomes the distance measure. In order to understand this definition, probably it is useful to look at one particular example. Let's see, we now are looking into different fruits and we're looking at different features associated with the fruit. And the first sample we have is apple, and we know it's round and it's sweet and a little bit sour and it's crunchy. And that's why you have yes, 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 yes to all the different features. And similarly, we answer the questions to banana and to orange. Now we know the answers as in the table. Now let's calculate the Hamming distance between different fruit types. First, we look at the apple versus banana. We know for apple and banana, they only agree with each other on the sweet dimension, on the sweet feature, so that the distance on this dimension is 0. However, the apple and banana disagrees on 3 other features or dimensions such as spear shape, sour, and crunchy. As a result, the distance between apple and banana is 3 based on the Hamming distance definition. Now let's look at another comparison, another distance calculation. Now we compare apple and orange. We know apple and orange, they're consistent on 3 features, so that for the 3 features, get the 0 distance. But it has disagreement on one feature, which is crunchy. As a result, the distance between apple and orange is 1 based on the definition of a Hamming distance. Another metric to measure distance or the upside similarity is called cosine similarity. It is often used for text or document analysis. Basically, the definition of cosine similarity is really the angles of two observations. Observations, now if they have n-dimensional features, can be expressed as vectors. Essentially, the cosine similarity measures the difference of two vectors' angles, as we see here. The benefit of doing so is rather than look at the magnitude of individual dimensions or distance based on the magnitude of features, now we'll look at the ratios between features in each vector or each observation. Because if two observations, two vectors has angle of 0, and the cosine 0 will give us 1.0, means those two vectors or two observations are perfectly correlated. In opposite, if two vectors or two observations have a degree of 90, then cosine will give a zero point 0.0 as a value, just due to the function of cosine, how it works. Now here, we can plot the thing for two-dimensional example, pretty convenient and give you an idea. In the math, go back to the cosine similarity definition. Denominators purely measure the distance of the magnitude of each vector relative to the origin, which has 0 on all dimensions. And we have that for vector A and vector B, or observation A, observation B. Then on the top, the numerator is purely the sum product or dot product of two vectors, for which the formulas are spread out in the appendix, just like this. If we have two vectors on n dimensions, and the sum product will be, we take the first element in the first vector times it with the second vector's first element. Then likewise, second element times second element and the last element to the last element. We sum them up. This is the definition of dot product, also called sum of products. Now let's go back to the cosine similarity. We talk about the definition. We talk about why the cosine similarity works. In this example, we have three documents we want to analyze. The first document, we have 100 counts of the keyword or the feature apple, the 40 count on the app, the second feature, and the 0 count on orange. For document 2, we have 100, 0, 30 respectively for the three dimensions or three features or keywords. And then for the third document, we have 10, 5, 0 accordingly on the three dimensions or three features. Using the cosine similarity, we can conclude that is document 1 and 3 are more similar to each other because we understand just by guess those two documents are something related to the technology to device. If we instead use the Euclidean distance to calculate the relationships of the three documents, we may conclude document 1 and 2 are more similar to each other. In fact, if our concern is about the topic, which documents have which topic, you probably agree that the cosine similarity is more appropriate in determining who are the neighbors. Because as you can tell, the document 1 and 3 are more likely associated with the technology and device, while document 2, even though it has the word of Apple, is more likely to be discussion the topic around the fruits. By now we have answered the first question, how to determine who are the neighbors. Now we come to the second question, how we determine the appropriate value of k, number of neighbors we should choose in applying the KNN algorithm. I can tell you the simple answer is if k is too big, it's not good. Or if k is too small, it's not good either. First, let's now explore, have some intuition check in case the k is too big. What is big, which is not big, is also relative to the sample data size. Let's say we're considering a k is really big. In this particular example, we only have two classes. They are either blue dots or red triangles. We only have this many training data we plot here. And now we have a new observation, which is denoted by green pentagon. The question is now, in which class should the new sample belong to? Again, if we look at the chart, look at the plot on the page, our visual system, our eyes and brain tell us our choice is the new sample, the green pentagon, is more likely to be associated with the blue dot category. However, if we set k equal to 6, which is kind of big relative to the data size we have, and if we make a circle and we'll notice that there are more red triangles than blue dots fall into the circle with the center as the green pentagon. If we use k equal to 6, the KNN algorithm will tell us the new sample should belong to the red triangle rather than the blue dot. This may not be right just based on our visual check. Now I think you get the point. When the k is too big, it may not be good. On the opposite, if k is too small, it's no good either. The most extreme case of k being too small is k just equal to 1. We only look at one neighbor for the prediction. The result of k being too small is the boundaries become very ragged. And because the k is too small, there's too much focus on the local nearby information so that it is blind to the overall pattern, overall distribution in the data. Again, let's check one example. We have three classes indicated by three different colors, kind of pink and purple and green. For each class, we have 60 observations in the data. Now, if we use k equal to 1 to determine the boundaries of three classes, we end up with this. The problem with this type of k equal to 1 setup is the whole boundaries becomes very ragged. For instance, this one, we see there's a pink around in the middle of many observations circled by the blue purplish area. And if we just use k equal to 1, if any new sample coming happen to be in this area, the conclusion will be this belong to the pink or the red. The question is that really the case? Because what if the particular data, the pink data in the training sample is just an outlier? If we focus too much on the particular instance, we may lose the big picture overall pattern in the data. So that's why if the k is too small, it's not good either. So what's the right way to determine the value of k? One good solution to decide the value of k is to use a technique called cross-validation. The formal name of this cross-validation is called the k-fold cross-validation. I want to call out immediately. The k in the k-fold cross-validation has nothing to do with the k in the k nearest neighbors. For this reason, I purposely make the k-fold its k in a lowercase and blue color, and the k in the k nearest neighbors is in uppercase and red color. Make it easier for you to distinguish. Now let me explain how the k-fold cross-validation works. what we do is we have training data. We'll evenly divide the training data into k subsets. Then we come to the loop, the outer loop. In the outer loop, we don't know what is the proper value of k for the knn. We're just going to loop through with k from the smallest 1 to the k to the biggest, the upper bound we want to apply. Let's see, we want to set the upper bound as k equal to 20 or the n to 20 as the boundary, upper boundary. Now we come to the inner loop. In the inner loop, we'll rotate the data. We'll rotate the way which go into the training and which go into the validation. Because the data are divided into the k subsets, in each rotation, we'll have k minus 1 as a training subset and only remaining 1 as the validation subset. Then given each rotation, we're using the k minus 1 as the training data to predict on the validation subset. Then we measure the prediction error for the validation subset. We can do this k times for each choice of the big red k in knn. In the end, when we finish all the interloops, we will calculate the average of prediction errors across all the k rotations. Since we also have outer loop, we loop through k from 1 all the way to n. In the end, we will see with which value of the big red k has the minimum average prediction errors, and that k value is the best k that we should choose for the k nearest neighbors. Now let's look at an example. In this example, we set the blue small k as 5, so we're doing 5-fold cross-validation. And we split data in 5 subsets. In rotation 1, the first 4 go into the training, the last one go to validation. And rotation 2, as you can see, the second last is head out for validation. Then thirdly, fourthly, and finally, you see the pattern here. We do 5 rotations because we have 5-fold cross-validation in this case. Later, we measure the prediction errors, the average of prediction errors based on the cross-validation and based on our outer loop, which we varies the big red k from 1 to all the way to 20, the upper bound we set. And by reading this plot, you can tell that is the minimum prediction error is achieved when the k, the big red k, is set to 7. So that tells us in this case we should set k, we should look at the 7 nearest neighbors to decide to use for our knn algorithm. That's all for today.